Okay, folks, get ready for a fun ride into VideoLLaMA 3. Ever wished your AI could get videos as well as you do? Minus the popcorn, of course. VideoLLaMA 3 is a new development in the field of multimodal AI. What sets it apart is its foundational approach. It focuses on understanding images first. The idea is that by mastering still images, the model can more effectively tackle the complexities of video. It uses a couple of key techniques to achieve this. Any-Resolution Vision Tokenization, which allows it to process images of any resolution, and a differential frame pruner, which helps it efficiently manage video data by reducing redundancy. We'll be discussing how this model works, its training process, and its performance on various benchmarks. Let's get started.
All right, let's kick things off with VideoLLaMA 3. This model marks a pretty significant leap in how machines understand images and videos. What's really cool about it is its focus on vision-specific principles. Instead of diving into massive video-text datasets, the creators argue that high-quality image-text data is where it's at. They believe that if a model can really understand images well, it'll be much better at grasping videos too. Makes sense, right? The training of VideoLLaMA 3 is broken down into 4 key stages. First up is the vision encoder adaptation. This is where the model learns to deal with images of different resolutions, ensuring it's flexible enough to handle all sorts of visual inputs. Next, we have vision language alignment. Here, the model learns to connect text and visual data seamlessly, pulling information from diverse sources like documents and charts. Then comes multitask fine-tuning, where VideoLLaMA 3 is trained on a bunch of tasks, like question answering for both images and videos. Finally, there's video-centric fine-tuning, which hones the model's ability to understand video content in depth. On the framework side, VideoLLaMA 3 does something clever. It adapts a vision encoder to process images dynamically and compresses video tokens. This makes the representation of videos more compact, which is great for saving computational resources while still being precise. Thanks to these innovations, VideoLLaMA 3 has achieved top-tier performance across benchmarks in both image and video understanding. As the paper's introduction points out, while LLMs have really pushed forward natural language intelligence, the next big step is extending that intelligence to multimodal capabilities, allowing for a more holistic understanding of the world around us. Moving along, VideoLLaMA 3 is described as a multimodal foundation model that handles static images and dynamic videos. The team's insight? Images are simpler to deal with and often of higher quality, so they provide a cleaner dataset to pre-train on. By mastering static images, the model is better equipped later to handle the temporal aspects of videos. Basically, sequences of correlated images over time. Look at the figure here, which compares VideoLLaMA 3's performance across several benchmarks like general video question answering, document comprehension, and multimodal math reasoning. You'll see it excels in tasks such as video MME and perception test for video-specific challenges. It also does really well in Math Vista for math reasoning and DOCVQA, document visual question answering, for document-based tasks. That versatility underscores its power to tackle both visual and multimodal challenges. A big part of modeling video content is dealing with temporal dependencies, plus the fact that many video text datasets just aren't as good. VideoLLaMA 3 counters this by leveraging its strong image-based core. The 4-stage training paradigm begins with adapting the vision encoder, so it plays nicely with large language models, capturing fine-grained details from images. Then they align vision and language, using annotated images, charts, and so on, to boost spatial reasoning. Focusing on quality data and adaptable architectures helps VideoLLaMA 3 bridge the gap between static and dynamic content. This sets the scene for more scalable and precise multimodal learning in the future. Now let's dive deeper into the model's 4-stage trainings. Stage 1 is vision encoder adaptation, where the model learns to handle all sorts of image resolutions and aspect ratios. They use scene images and optical character recognition (OCR) data to refine how the encoder extracts visual details. Stage 2 is vision language alignment. Here, the model sees images paired with rich textual annotations, things like bounding boxes, documents, and charts. This helps it understand spatial layouts and fine-grained visual features. Then, in multitask fine-tuning, the model tackles tasks like video captioning and question answering. Interestingly, the video caption data doesn't just boost video understanding, it also improves image-based tasks, revealing a neat synergy between image and video learning. The final step, video-centric fine-tuning, teaches the model to compress video tokens more effectively. That way, the model becomes efficient at handling dynamic content and ensures minimal computational overhead. For instance, they use techniques like rotary position embedding to handle different image shapes and resolutions without losing much information. All in all, this vision-first approach helps the model nail state-of-the-art scores in image benchmarks, like chart understanding and math reasoning, while also delivering precise temporal reasoning and grounding in video tasks. Next up is a look at two major innovations behind VideoLLaMA 3's pipeline. First, there's Any-Resolution Vision Tokenization, AVT. This mechanism converts images and videos, no matter their resolution, into flexible token sequences. Unlike methods that force inputs into a fixed size, AVT lets the model process images of different shapes and sizes more naturally. That flexibility cuts down on information loss and improves the model's visual understanding across diverse inputs. The second big piece is the differential frame pruner, diff-FP. As you might know, many frames in a video look nearly identical, which causes a lot of redundancy in token generation. Diff-FP calculates differences between consecutive patches and prunes out the ones that barely change. This means the model doesn't waste time on repetitive details. Instead, it focuses on what's genuinely different from frame to frame. Together, AVT and diff-FP make VideoLLaMA 3 super flexible and efficient. It can handle both images and videos at arbitrary resolutions, and it can intelligently compress long videos so it doesn't get bogged down. This approach not only streamlines the model's computation, but also helps it nail both static and dynamic tasks. Pretty neat, right? Look at the methodology illustration here. Notice how the model relies on large-scale image pre-training to jumpstart video comprehension. It's a reminder that combining innovative data processing with a thoughtful model architecture can really move multimodal understanding forward. Let's talk more about diff-FP. When the model processes videos, it turns each frame into tokens. But because many frames are visually similar, you end up with a boatload of redundant tokens, wasting computation. Diff-FP, differential frame pruner, solves this by measuring how different each patch is from its counterpart in the previous frame. If a patch hasn't changed much, out it goes. This way, the model only focuses on tokens that actually matter. On the dataset side, the team created an image recaption dataset called VideoLLaMA 3 How did they clean it? First, they filtered out images with weird aspect ratios to avoid skewing the model. Then, they used an aesthetic scoring model to throw out low-quality images. Finally, they applied a text-image similarity check so the captions truly matched each image. The result? A cleaner, more reliable dataset that helps VideoLLaMA 3 learn effectively. Combine diff-FP's efficient pruning with that rigorous data pipeline, and you get a model that's especially good at understanding long-form videos without burning through too many computational resources. Building on that, let's see how the team put together the full VideoLLaMA 3 dataset, 7 million high-quality image caption pairs. They took visual features derived from contrastive language image pre-training, CLIP, then used a nearest neighbors, KNN, algorithm for clustering. From each cluster, they carefully picked images to ensure diversity. Next, they recaptioned these images with advanced language models, generating everything from succinct to more descriptive annotations, depending on training needs. Now, how is VideoLLaMA 3 actually trained? It uses 4 core components: a vision encoder, a video compressor, a projector, and a large language model, LLM. The training follows 4 stages. First is vision encoder adaptation to handle dynamic resolutions. The projector aligns the extracted features with the LLM's embeddings. Second is vision language alignment, where the model sees multimodal data and learns how images and text interact. Third, multitask fine-tuning exposes the model to question answering and video captioning tasks. This is crucial for helping it follow instructions and juggle both image and video content. Lastly, video-centric fine-tuning zeroes in on dynamic, time-based data, refining the model's ability to parse temporal information. All these steps make VideoLLaMA 3 a well-rounded, multimodal powerhouse. Data organization is everything in a project like this. Look at Figure 5 here for a visual on how the team formats different data types. For image sequences, tokens are separated by new lines, merging image and text in a single sequence. For video sequences, timestamps precede each frame token, with commas separating frames and new lines to mark the end. This explicit structure helps the model tell apart text tokens from video tokens. In a streaming scenario, video and text tokens are interleaved, so the model can respond in real time with contextualized outputs. Check out Table 1 here, which lists datasets used in the vision encoder adaptation stage. They combined over 11 million scene images, nearly 1 million scene text images, and close to 3 million documents. Each dataset underwent a thorough cleaning process to preserve high-quality data. This ensures the model learns from the most relevant, crisp examples, boosting its ability to handle varied content, including tricky interactive streaming tasks. Now let's talk about the vision language alignment stage. This phase exposes the model to a wide variety of top-notch data. For scene images, the team pulled over 12 million samples, mixing real annotations from datasets like COCO 2017 and Object 365 with high-quality, AI-generated captions. That way, the model learns from both authentic and richly detailed text pairs. For scene text images, they used resources like BLIP3 Optical Character Recognition (OCR) and COCO Text, offering examples in both Chinese and English. Captions here include bounding boxes, giving the model spatial context about where text appears in an image. Document datasets like SynthDOG and PDFA-ING-WDS provide highly accurate text representations with minimal noise or annotation errors. They also included fine-grained data and chart samples for even more detailed visual analysis, plus plenty of pure text data to reinforce language comprehension. This balanced mix ensures the model smoothly integrates visual and linguistic info, paving the way for advanced multimodal reasoning. Next, let's discuss multitask fine-tuning. This stage strengthens the model's ability to follow instructions across a broad range of visual and textual tasks. They gathered datasets that span 6 main visual categories: general image text, documents, charts/figures, OCR, grounding, and multi-image. Each category targets a specific angle of visual comprehension. For instance, general image text data helps the model understand entire scenes, while document sets like document visual question answering, DOCVQA, specialize in extracting structured text from images. Charts and figures add complexity, requiring the model to interpret data visualizations. OCR datasets hone its text recognition chops, focusing on intricate or cluttered layouts. Grounding tasks use bounding boxes to link textual descriptions to actual objects, boosting localization skills. They also include video data for an extra layer of temporal reasoning. And a bunch of text-only data rounds out the model's language understanding. By exposing it to this variety of tasks, the model becomes more flexible and can adapt to all sorts of multimodal challenges. Now, onto video-centric fine-tuning. Here, they really emphasize the model's skills in handling dynamic content. A broad range of datasets feeds into this stage, starting with general video data, about 3.03 million examples. These sets come with captions and time-based data to teach the model how events unfold. For streaming video, datasets like ActivityNet and Ego4D narrations simulate real-world video streams, one frame at a time. This is trickier because the model has to maintain context across time. Temporal grounding sets take it further by focusing on the relationships between events. By including a variety of static image-only and text-only data, the team ensures the model retains strong single-frame understanding and language skills while also gaining advanced temporal insights. They even use in-house temporal grounding data to capture subtle shifts between frames. All of that means VideoLLaMA 3 can tackle complex video tasks, reading both time and space in ways older models might struggle to do. Continuing with video-centric fine-tuning, they assembled about 2.7 million video-centric conversations from sources like LLaVA Video and VideoGPT. To enrich that, they synthesized dense captions and QA pairs from Panda70M, spotlighting temporal reasoning, spatial understanding, and object descriptors. This yields super detailed annotations that train the model to dissect video content thoroughly. Streaming video is introduced by segmenting frames with dense captions in sequence. Check out datasets like ActivityNet or Ego4D for that. They clip the video in 2-minute intervals, so the model learns how to deal with multi-turn chats in a near real-time setting. They also incorporate data with event timestamps to sharpen the model's capacity for temporal detection. Implementation details like using a cosine learning rate scheduler, limiting vision tokens, and downsampling large datasets all help with efficiency. They align visual tokens for both video and images by interpolation. And they pick frames at 1 frame per second to standardize the content while retaining enough detail. Put it all together, and you get a model that's well prepared for complex, real-world, multimodal tasks. Time to see how VideoLLaMA 3 performs on images. First, they compare it to other 2B parameter models like Intern VL 2.5 and QN 2VL. They run 4 main tests: document and chart understanding, mathematical reasoning, multi-image tasks, and general knowledge-based QA. Check out some of these results. On document visual question answering, DOCVQA and OCR Bench and OCR Benchmark, it does extremely well. Scores like 91.9 on DOCVQA. That's pretty impressive. Next, for math reasoning, they use MathVista, where the model's ability to parse equations in images is tested. Again, it comes out on top. In multi-image scenarios, tasks from MMMU Pro measure how well the model can understand relationships across multiple images. And it scores about 28.6. And for general knowledge QA tasks like real-world QA or AI2D, it achieves high accuracy, showing that it can handle a broad range of questions about real-world or diagram-based content. All of that puts VideoLLaMA 3 at the head of the pack among 2B parameter models for image-based tasks. Now let's jump to the 7B model evaluations. Again, VideoLLaMA 3 faces off against models like QN2VL. For document and chart tasks, it shines on DOCVQA and OCR Bench, hitting a fantastic 94.9 on DOCVQA, beating out competition like QN2VL. Then, for math tasks like MathVista, it takes the lead with a score of 67.1. That indicates it can handle visually presented math problems with logical accuracy. On multi-image sets, such as MMMU Pro, VideoLLaMA 3 gets a leading 33.6, showing strong reasoning across multiple images. Finally, in general knowledge QA with benchmarks like real-world QA and AI2D, it continues to provide solid, context-rich answers. These strong results confirm that VideoLLaMA 3 stands as a top-tier 7B scale model for multimodal reasoning and visual textual integration. Let's see how it does on video benchmarks. VideoLLaMA 3 shows robust performance across different tasks. It leads in general video understanding, dominating benchmarks like Video MME and Perception Test. For instance, it achieves 68.0 on Perception Test, indicating it can parse complex video scenes. When looking at long video comprehension, it handles benchmarks like MLVUDev and Long Video Bench very well, scoring around 65.4 on MLVUDev. This reflects its ability to extract meaningful content from extended video sequences. And in temporal reasoning, it pulls off a standout 81.1 on NextQA. Better than any other model tested, that means it's great at understanding the sequence and timing of video events. Overall, these video scores confirm that VideoLLaMA 3 isn't just about images, it excels in dynamic visual understanding too. Focusing on the 7B parameter scale again, VideoLLaMA 3 competes with baselines like QN2VL and InternVL 2.5. For general video understanding, it does great on Video MME and MV Bench, earning scores of 66.2 and 69.7 respectively. If you're curious about how it handles longer sequences, it racks up a 73.0 on MLVUDev, leading the pack. Its temporal reasoning is especially impressive. On NextQA, it hits 84.5, which really highlights its knack for following event order and logic. So, whether it's short clips or extended footage, VideoLLaMA 3 proves it can handle video-based tasks reliably at the 7B scale. Digging a bit more into the details, VideoLLaMA 3 continues to excel in various video categories. For general video understanding, you'll see numbers like 59.6 on Video MME when there are no subtitles, and 68.0 on Perception Test. For long video tasks like MLVUDev, it reaches 65.4%, which is impressive for multi-minute or even hour-long content. While it scores 40.4% on LV Bench, slightly lower, it's still above many other models. It truly stands out in temporal reasoning tasks such as Temp Compass, 63.4%, and NextQA, 81.1%. This means it can follow events in sequence really well. There's also a neat example here of chart image understanding, where VideoLLaMA 3 interprets stock trend charts, identifying signals like potential investment opportunities. This underscores its blend of vision and reasoning. In short, it handles both video comprehension and chart-based data, making it versatile for real-world applications. Let's shift gears and look at some technical findings. An ablation study compared different pre-trained vision encoders, like CLIP, Contrastive Language Image Pre-training, DFN, and SIG-LIP, to see which worked best with LLMs. SIG-LIP came out on top across all benchmarks, especially in tasks like GQA, a dataset for visual reasoning, and document visual question answering. This shows how critical it is to pick the right vision encoder that aligns well with language embeddings. They maintained the original resolution of visual inputs as per each encoder's pre-training. The overall training had 3 main steps: aligning the chosen vision encoder on big representation datasets like COYO, then tuning with large multimodal sets, and finally fine-tuning on task-specific instructions. SIG-LIP gave them a solid edge in tasks demanding chart, document, or intricate image understanding. So, a carefully aligned vision encoder can really supercharge a multimodal language model's performance. That's a key takeaway from this study. Moving on to chart-based analysis, we have some cool examples. The first is a volatile stock chart where VideoLLaMA 3 notices sharp price swings and references a technical indicator called Moving Average Convergence Divergence, MACD. It also sees lots of red candlesticks, indicating selling pressure, and advises caution. It even suggests looking for more stable investments. Pretty insightful for a machine, right? In the second example, the chart compares AI models by performance and computational load. Models like QN2VL7B and DeepSeek-VL2 are plotted against average performance and activated parameters. VideoLLaMA 3 points out that QN2VL7B is the strongest in pure accuracy, but DeepSeek-VL2 is better if you consider efficiency. So it's evaluating trade-offs, which is pretty handy for model selection. These instances highlight how VideoLLaMA 3 can dissect complex visual data to offer thoughtful, data-driven insights. How does the model handle OCR, optical character recognition, and document images? Let's take two examples. First, it critiques a fall festival poster. The design has a few flaws. No visual hierarchy, not enough event details, and a dull color scheme. VideoLLaMA 3 suggests clearer font sizing, including key info like dates and location, and adding bright autumn colors or a pumpkin graphic to really pop. Solid design tips. In the second example, it parses a medical document on femoral headwear rates. The model extracts details about how different materials, ceramics or zirconia, are more resistant compared to metal. It even cites key findings from various studies, showing it can handle dense technical content and produce an informative summary. So, whether it's helping with design improvements or diving into scientific data, VideoLLaMA 3 can be a versatile assistant for visual text. Next, let's see the model in action with multiple images. In one example, it compares two animals, noting that one is brown with a white neck and the other is yellow with black stripes plus a red back. That's a nice, detailed contrast. Then it analyzes a document about sports trials, identifying rules like grading in August or September 2021, which divisions need to participate, and age restrictions. Finally, it concludes a short story based on three sequential images: Jack and Lizzie playing in a park, their parents Martha and Jeff searching for them, and the happy reunion. This demonstrates how the model ties visuals together into a coherent narrative. Now let's talk about general knowledge and context-based analysis with visuals. First, there's a basketball scene that the model recognizes as a free throw. It picks up on the player's position at the free throw line, the crowd, and other visual cues. Then it describes the Mona Lisa, calling attention to its Renaissance style, famous smile, and cultural impact. That includes how it put the Louvre Museum in the spotlight and influenced art history. Lastly, there's a space-themed video with an adorable twist, a group of puppies in astronaut suits. The model notes a shot of Earth from space before zooming in on the cute pups. Combining a sense of narrative with visual details makes these examples feel lively and engaging. In these examples, VideoLLaMA 3 tackles detailed video scenes. One scenario is a backyard tour, mentioning specific objects like a couch, a TV, and a kitchen with stainless steel appliances. Another sequence has a keyboard whose keys vanish one by one, and the model identifies the digit 1 as the final remaining key. It even describes a whimsical video of bears calmly eating sushi in a forest, capturing the unexpectedness of that scene. There's also a bubble unicorn blowing bubbles near a rubber duck, which the model describes in a fun, imaginative way. Finally, it identifies an athlete with jersey number 184 as the winner in a sports competition. Overall, it handles both the mundane and the fantastic with ease. Here we see how VideoLLaMA 3 manages video event grounding and context comparisons. First, it narrates a travel montage in Russia, describing an icy tightrope walk, scenic landscapes, and bustling cities, all accompanied by music. Next, there's a scene of a man pouring cola into a cup, and the model pinpoints the action's start and end timestamps over a roughly 13-second span. Pretty precise temporal tracking. Then it compares a video featuring a kitten and chick cuddling with an unrelated still image of a woman walking at night. The model notes that the two pieces of media share no connection, showing it can differentiate distinct visual contexts. This demonstrates solid temporal detection and the ability to judge relationships between different types of visual input. Let's take a quick step back and talk about how multimodal large language models, MLLMs, have evolved to handle video. Early models struggled with long input lengths and tricky temporal aspects. Researchers tried solutions like spatial temporal token pooling or specialized video encoders. More recent techniques unify multiple data types, video, audio, text, into a single framework. Adding instruction tuning with combined datasets has made real-time tasks like live captioning easier. Examples include QN2VL and InternVL, which use big-scale architectures and extensive training sets to improve video performance. Some newer models also mix different design philosophies, like Mamba-based or transformer-based approaches, to handle long sequences more efficiently. Altogether, these developments pave the way for cross-scenario performance in tasks spanning vision, text, audio, and beyond. VideoLLaMA 3 fits right into this landscape, emphasizing the value of a solid image core and careful integration of video data to push the boundaries of multimodal understanding. Finally, let's consider what VideoLLaMA 3 does well, where it falls short, and where it might go next. Its dynamic resolution handling and token compression are huge pluses. These let it operate across diverse image or video formats, making it flexible for real-world applications. By training on multiple tasks like Q&A or captioning, it builds a well-rounded understanding. However, challenges remain. Video text datasets can be limited in both quality and variety, so the model might not yet generalize to every domain. Real-time video processing also remains expensive, so something like live analytics could slow down. And though VideoLLaMA 3 focuses on vision and text, other modalities like audio or sensor data haven't been fully explored. Where do we go from here? Improving dataset quality with richer annotations could help. Real-time optimizations, like parallel processing or more refined tokenization, could reduce latency. Extending to audio and other modalities might also open up new capabilities. And post-training methods like reinforcement learning could align the model's outputs more closely to human preferences. That wraps up the core ideas around VideoLLaMA 3. Thanks again for sticking around, and happy exploring!